In the last lecture, we were discussing vector forms for the mass and energy conservation equation. Okay. So, the mass conservation equation had this form, okay, partial C by partial T, okay, plus the divergence of V c is equal to minus the divergence of the flux plus the source. The flux is given by Fick's law for diffusion, and if you substitute that, you will get partial C by partial T plus divergence of V c is equal to divergence of d grad C plus the source. If the diffusion coefficient is a constant, partial C by partial T plus del dot V c plus the source. Okay. So, those are the equivalent ways of writing the conservation equation, where we had got the expressions for the gradient, the divergence in a general coordinate system. Okay. Grad C was equal to E a by H a partial C by partial x a plus E b that was the gradient. The divergence of a vector was defined as 1 by where x a and x b and x c are the coordinates, E a, E b and E c are the orthogonal unit vectors, and H a, H b and H c are the scale factors. Okay. And you can put this in to get the Laplacian del square C is equal to so these are the gradient divergence in the Laplacian expressed in component form in a coordinate system with coordinates x a, x b and x c, unit vectors E a, E b and E c, and scale factors H a, H b and H c. The extension to heat transfer is quite easy, rho C p times partial T by partial T plus divergence of V into T is equal to the divergence of K grad T plus the energy source. Okay, so, that is the extension to heat transfer. Here we have assumed that rho C p is a constant, which is a good approximation in normal situations. Dividing throughout by rho C p, the equation becomes partial T by partial T plus the divergence of V times T. Is equal to divergence of alpha grad T plus S e by rho Cp, where alpha is the thermal diffusivity. Okay. And if the thermal diffusivity is independent of position or time, then you can write this equation as partial T by partial T plus divergence of V T is equal to alpha del square T plus So, you can get the energy balance equation by substituting T for C in the mass conservation equation, alpha for the diffusion coefficient, and the energy source by rho Cp for the mass source in the mass conservation equation. Okay. So, the two are entirely equivalent. Next, we will go on to the fluid. Okay. Mass and momentum. Equations. Okay. The fluid mass equation is the equation for the conservation mass for the entire fluid, not one particular component. This the fluid mass conservation equation is written for the density of the fluid rho, which is the mass per unit volume of the entire fluid. Okay. For the entire fluid, if the velocity is the center of mass velocity of the fluid, right. If the velocity is the center of mass velocity of the fluid, there is no relative velocity of there is no diffusive component of the velocity, because the velocity itself contains the center of mass velocity of the fluid, which is the total momentum divided by total mass, okay, within a volume, within a differential volume. Okay. So, therefore, for a single component or for the entire fluid, which is the sum of all the components, there is no relative diffusion. Only if you have one component moving relative to the other will you have diffusion. When you consider the fluid as a whole, there is no motion relative to the center of mass. Okay. Therefore, there is no diffusion term in the equation for the fluid, and mass conservation requires that, okay, partial of rho by partial T plus the divergence of rho times V has got to be equal to 0. Okay. So, that is the mass conservation equation for the fluid, because there is only one velocity here. You do not have different velocities for different species in this particular case, because you are considering the entire fluid as a whole. Okay. So, this is the conservation equation. Just as we had done for the case of the concentration field, the second term on the left can be expanded by product rule. Okay. Equal to 0. Okay. And recall that these first two terms here are the convected derivatives. Okay. These first two terms here are the convected derivatives. Therefore, I can write this as d rho by dt plus rho times the divergence of the velocity is equal to 0. Incompressible fluid. For an incompressible flow, d rho by dt is equal to 0. That implies that the divergence of the velocity is equal to 0. Okay. If the flow is incompressible, so that the density is a constant, then the derivative, time derivative or the convected derivative of the density has to be 0. Okay. And if you substitute that into this equation, this basically tells you that the divergence of the velocity is equal to 0. Okay. So, a flow is incompressible typically if the flow velocity is much smaller than the speed of sound. Okay. A flow is incompressible typically if the flow velocity is much smaller than the speed of sound. and that is true in most practical applications that we consider. And therefore, throughout this course, we will consider the fluid to be incompressible, or the divergence of the velocity has to be 0. Okay. What does it mean that divergence of the velocity is equal to 0? I had explained for you the physical meaning of divergence, okay, over here. Okay. At a differential volume locally, okay, if I consider a surface around that volume, take the velocity vector dotted with the unit normal and integrate over the surface, I get the divergence of the velocity. I have to divide by the volume, of course. What we mean by saying that the velocity does not have any divergence, that the velocity is divergence free, is that the divergence, there is no divergence or convergence of the velocity field at a point. Okay. And that is because there has to be no mass, no creation or destruction of mass within this differential volume. If the mass is a constant, okay, if the mass within a differential volume is a constant and the density is a constant, that means that the volume occupied by that fluid has to be a constant. Okay. There cannot be any volumetric expansion or compression when the density is a constant, okay, because we know that mass is a constant and therefore, there cannot be any volumetric expansion or compression. Okay. You know that the density is equal to the mass times the volume of the fluid. Okay. The density, I am sorry, I should write it the other way. The mass is equal to the density times the volume, okay, which means that the rate of change of mass within a particular volume, okay, dm by dt is equal to rho dv by dt plus v d rho by dt. Okay. And since there is no change in mass, mass cannot be created or destroyed, this has to be equal to 0. Okay. And from that you will find that 1 over v dv by dt is equal to minus 1 over rho d rho by dt. Okay. So, minus 1 over rho d rho by dt is the rate of volumetric expansion or compression. Okay. Okay. And we know that minus 1 over rho d rho by dt from this equation, okay, from this equation, minus 1 over rho d rho by dt, this is equal to the divergence of the velocity. Okay. So, the divergence of the velocity gives you the rate of volumetric expansion or compression divided by the volume itself, okay, of the fluid at that location, the rate of volumetric expansion or compression of the fluid at that location. Okay. For an incompressible fluid, if the mass is conserved and the density is a constant, you cannot have volumetric expansion or compression, and because of that you cannot have, okay, a divergence of the velocity from a point. Okay. And that is the reason why the divergence of the velocity is 0 for an incompressible flow. Okay. So, the velocity has no divergence for an incompressible flow, and this equation del dot v is equal to 0 is the Navier-Stokes mass conservation equation. Okay, for an incompressible fluid. Okay, this is the Navier-Stokes mass conservation equation. So, divergence of velocity is equal to 0. Okay. Now, if we consider a two-dimensional coordinate system, if we consider a two-dimensional coordinate system, x and y. The mass conservation equation is that partial V x by partial x plus partial V y by partial y is equal to 0. This is one relation between the two velocity components x and y, and that means that I can reduce this to just one function. Okay, I can reduce V x and V y both to just one function. The way this is done is to write V x is equal to partial psi by partial phi partial y, V y is equal to partial where this function psi is called the stream function. Okay, where psi is what is called the stream function. Okay. You can see that with this substitution, V x is equal to partial psi by partial y and V y is equal to minus partial psi by partial x. If I substitute that into the mass conservation equation, the mass conservation equation is identically satisfied. Okay. Okay, so, therefore, the definition of the stream function ensures that if I express the velocity in terms of the stream function, the mass conservation equation is identically satisfied. Okay. Now, what is the meaning of this function, the stream function? Okay, so, let me give you some idea of that. Okay. If I have 2 points A and B, okay, and have some path along this from A to B, okay, with some unit normal n. Okay. In 2 dimensions, I have some contour with a unit normal n, okay, which is the normal to the contour. Okay. I can ask what is the total amount of fluid mass that is crossing this contour per unit area per unit time. Okay. This is 2 dimensional, so you have to consider it as the total fluid mass, the total fluid volume that is crossing this contour from left to right due to the flow velocity. Okay. Due to the flow velocity, what is the total volume of fluid, volumetric flow rate of fluid between these 2 points A and B. Okay. There is a volume that is transported across this contour per unit length perpendicular to the plane, because note that this is 2 dimensional. So, it is basically a volume per unit length perpendicular to the plane per unit time. Okay. So, how do we calculate that? Okay. So, the volumetric flow rate, okay, is equal to integral between the 2 locations x a, x b of the differential displacement d s here. Okay. I will take a small differential displacement delta s along this contour, delta s, okay, times the component of the velocity perpendicular to the contour n dot v. Okay. Note that it is only the component of the velocity perpendicular to this contour that results in fluid crossing this contour. The other component parallel to this contour does not result in any flow across this contour. Okay. So, this is basically going to be the flow rate Q, okay, for the fluid crossing this contour. Okay. So, let me expand this out. Okay. So, this is the contour, this is the differential displacement delta s, okay, and this is the unit normal n. Okay. And in this coordinate system, the unit normal has component n x and n y. Okay. The vector parallel to this contour is the unit tangent. Okay. The vector parallel to this contour is the unit tangent t. Okay. The vector parallel to this contour is the unit tangent t, okay, and that will have components, okay, in this case t x and component in this direction T y. So, T is perpendicular to n, okay. T is perpendicular to n, and what that implies is that okay, nx Tx plus ny Ty has to be equal to 0, and both of them have to be unit vectors. Okay. So, nx square plus ny square is 1 and Tx square plus Ty square is equal to 1. Okay. And you can easily see for that reason, as well as from this geometric construction, you can easily see that the components satisfy Tx is equal to ny, Ty is equal to minus nx. Okay. This way both of them are unit vectors with nx square plus ny square 1 and Tx square plus Ty square 1, and the product Tx nx plus Ty ny will turn out to be 0, okay, and therefore, they are perpendicular to each other. So, let me write this in terms of the components, okay, xa, okay, nx Vx plus ny Vy. Okay. Now, for these components, right, I will substitute in terms of the unit tangent from here. For the components, I will substitute in terms of the unit tangent from here. For the velocities, okay, I will substitute in terms of the stream function from here. Okay, I will substitute in terms of the stream function. Okay. So, this is integral between x a and x b, okay, ds. Okay. Nx is equal to kindly, there is a mistake here, kindly note that down. Okay. Tx is negative if ny is positive. Okay. Tx is negative if ny is positive. So, I should write Tx is equal to minus ny. Okay. Tx is negative in the minus x direction, as you can see this vector is in the minus x direction if ny is positive. So, Tx is equal to minus ny, whereas Ty is equal to nx. Okay. Kindly note that mistake. Okay. So, in this case nx is equal to Ty, okay, and Vx is equal to partial psi by partial y, okay, plus ny is equal to minus Tx, okay, and Vy from here is equal to minus partial psi by partial x. Okay. And you can easily see this becomes Ty partial psi by partial y plus Tx partial psi by partial x, which is the same as integral x a to x b ds into T vector dotted with grad psi. Okay, grad psi is in this two dimensional system is Ex partial psi by partial x plus Ey partial psi by partial y, and T is Tx Ex plus Ty Ey. So, if you dot the two, you will get Tx into partial psi by partial x plus Ty into partial psi by partial y. Okay. This T times ds is the vector displacement. Okay. This T times ds is the vector displacement along this contour. Okay. T times dx is the vector displacement, okay, along this contour. Delta s is this distance travelled, T is the tangent, and therefore, T times delta s is the vector displacement. So, I can also write this as integral x a into x b of dx along the path, okay, the vector displacement along the path dotted with grad psi. And this should be familiar to you. This is the integral relation for the gradient. Okay, this is the integral relation for the gradient. This is equal to the difference in the stream function at the location B minus the stream function at the location A. Okay. So, this is the physical interpretation of the stream function. The difference in the stream function between two locations is the total amount of fluid crossing any contour joining those two locations, and the amount of fluid crossing any contour between those two locations is exactly the same. That is V dot n to the where n is the unit normal to the contour. V dot n integrated over the contour is exactly the same for any contour, and that is equal to the difference in the stream function between those two locations. So, that is the physical interpretation of the stream function, okay, for two locations. Okay. The stream function can also be defined for a cylindrical coordinate system if it is two dimensional. Okay. So, if I have a cylindrical coordinate system, okay, axisymmetric, so that there is no variation in the I'm sorry, a cylindrical coordinate system which is which does not vary in the z direction, okay, which is described by the r and phi, okay, the angle r and phi, a polar coordinate system. Okay, if you have a polar coordinate system, we had found out that the divergence of the velocity, okay, del dot v is equal to 1 by r d by dr of r v r plus 1 by r partial v phi by partial phi. Okay. For a two dimensional flow which has only components in the r and the phi directions. Okay. This has to be equal to 0 for an incompressible flow. Okay. This has to be 0 for an incompressible flow, and you can define the stream function by V r is equal to 1 by r partial psi by partial phi. V phi is equal to minus partial psi by partial r. Okay. If you define the stream function in this way, the mass conservation equation is identically satisfied for this stream function. Okay. So, that is what is the extension of this for a polar coordinate system. Okay. And similarly, you can do this for an axisymmetric spherical coordinate system. Okay. If there is no variation of the field variables with respect to the phi coordinate, that is, there is no variation in the meridional direction, okay, then the mass conservation equation in this case becomes 1 by r square d by dr of r square v r plus 1 by r sin theta. Okay, from the definition of the divergence, if it is there is no dependence on the azimuthal coordinate, and in this case you can define the stream function by the relations So, these are the extensions of the concept of the stream function for two dimensional flows for a cylindrical and a spherical coordinate system. So, to summarize, I had said that the divergence of the velocity has to be 0 for an incompressible fluid. Okay. For a general compressible fluid, the mass conservation equation is d rho by dt plus the divergence of rho v is equal to 0. If the fluid is incompressible, the density is not a function of time. Divergence of the velocity is 0. That means there is no net divergence of the velocity vector from any location. Okay. That conserves volume. Okay. And if the mass is also conserved, okay, that conserves volume. If density is a constant, then mass is also conserved, okay, in that case. Okay. So, the divergence of the velocity is the rate of expansion or compression, volumetric expansion or compression divided by the volume. Okay. This is the divergence of velocity, rate of volumetric expansion or compression divided by the volume. Okay. For a two-dimensional system, both components of the velocity can be expressed in terms of one scalar function, the stream function, and this stream function has the physical interpretation that the difference in stream function between two locations gives you the rate at which fluid is crossing any contour between those two locations, the flow rate of fluid across any contour between those two locations per unit length in the direction perpendicular to the flow, okay, because this we are considering a two-dimensional system. So, this is the mass conservation equation. Next, we have to proceed to the momentum conservation equation. Before that, I have to define for you the stress and the rate of deformation tensor. These are different from the definitions of the flux and the concentration gradient that we had earlier. In those cases, flux and concentration gradient are vectors. In this case, the stress has two directions associated with it, direction of momentum and direction of transport. It is a second order tensor. The velocity gradient is also a second order tensor. We will first examine the physical meaning of these second order tensors before we proceed to the momentum conservation equation and Newton's law for viscosity expressed in tensor form. I will continue this in the next lecture. I will see you then.